आवाज़ आ रही है सबको? अच्छी, ठीक है। अच्छा, पहले कुछ चीज़ें पहले तय कर लें इससे पहले कि लेक्चर शुरू करें। सवाल ज़रूर पूछें जहाँ पर कोई चीज़ पूछनी है, सवाल आधा इल्म है, ठीक है। तो इसलिए आपने जहाँ पर आपको लगे कि कोई चीज़ ऐसी है जो नहीं समझ आ रही या मैं गलत कर रहा हूँ, जो कई जगहों पे होगा, तो यू आर फ्री टू इंटरप्ट एट एनी टाइम। इंतज़ार नहीं करना कि लेक्चर ख़त्म होगा तो फिर आप सवाल पूछेंगे। ओके, सो शुरू करें सर। The subject which I am going to cover is the complex variables. I did some survey from students who came from different universities, and they told me that this is kind of an ignored topic in most of the universities, including in my own university recently, you know, because they said that they have this topic towards the very end of their semester, and they used to have 2 to 3 lectures on that topic. So I'll try to cover most of the things in this course along with some applications, because you know that the complex variables, they have huge applications. The subject which Essen is talking about, the quantum mechanics, it is full of these complex numbers. So complex numbers, complex variables, they are the very core of the subjects, you know. And the outline of this course is maybe let me write it. I'll talk about simple introduction, very basic that you know. In the first lecture is just the introduction and the concept of the complex plane. Of complex plane, I can write it as a C plane, right? In the second lecture, probably I'll talk about the analytic functions. Sometimes we call them the holomorphic functions also, so I'll just use these names back and forth depending upon the convenience, and that comes quickly in my mind. So I'll talk about the analytic functions and their relations to the and the Cauchy-Riemann conditions, because these are the conditions that if these conditions this is a set of conditions, and if these conditions are satisfied, the function is continuous and analytic. And we'll see that not every function is analytic. And then in the same lecture, I'll try to talk about the entire function also. That if a function is analytic in some complex plane, everywhere in the complex plane for modulus of z is less than infinity, then this is an entire function. And then I'll talk about the integrability of the function, and then you can say that integral of a complex function, of a C function, and Cauchy's theorem. This will be possibly in the third lecture. And you know that in physics, for example, we deal a lot with the series expansion. What happens if we have the argument of some function to be the complex function, how we can expand the things in the series. And we can talk about 2 types of series. One is the Taylor series, and then I'll talk about the Laurent series. And you see that this Laurent series, this will have the inverse functions of the complex variable. If I call it as a z, let's say, it means this function, suppose it is 1 over z, and if z is equal to 0, this becomes infinite. So it means there is a point where the function is not analytic, right? So it means it has a link with the entire function also that I'm planning to discuss in the second lecture, and in the fourth lecture I'll talk about the Laurent series. And you know that what happens if the function is 1 over z? It can be 1 over z square, it can be 1 over z cube, it can be 1 over z to the power n. It means this 1 over z is a singularity, and the singularity we call it as a pole. It means there are different orders of pole. And then in the same lecture, I'll talk about the orders of polar poles and their order of poles, and how to extract the residue. I mean, from the pole, how I can extract the residue. And after all this, the most important topic is the residue theorem. It is such an important topic that sometime we call complex variable as a calculus of residues, because these residues we have to apply this theorem whenever we calculate the Green's function, because the Green's function has some, for example, even in the simple quantum mechanics, if you have 1 over E minus E naught, E squared minus E naught squared, X squared minus A squared, then it has a pole at X is minus A and X plus A. How to remove these poles in the given range? This can be done with the help of the residue theorem, and I'll talk about some of its applications. So, and then of course after the residue theorem and its applications, I'll talk about the Jordan's lemma, and then I'll tell you this because this Jordan lemma, once we use this lemma, then we can do the contour integration, and from this we can understand the causality also. And then this will be probably this will be the topic of 6th lecture. If everything goes as per plan, then in the 7th lecture I'll talk about then what is the analytic continuation, and you can say that, and then linear response. I'll talk about this if something happens at one point, and then I will relate it with the frequencies, and naturally after that we have the last topic to be the dispersion relation. So with this, I think this is more than enough if we can cover it. I'll try my level best to go through all the topics, and in between at some points I'll talk about branch cuts, because if for a complex variable, today I'll tell you that there are the possibilities to have a multi-valued function, and in order to have remove some of the points, we use the idea of the branch cuts and the other stuff. So I'll discuss this in detail because I don't want to talk about it right now, and I'll try to discuss it in 6th lecture probably if I'll get some time. Otherwise, I'll give you a hand-waving argument about that, because this is more than enough if we can cover it. And of course, at the end of every lecture, I'll try to tell you if the contents of this lecture are applied in some problems in physics, right? So all of you know the complex number, right? A number in 2 dimensions. We used to have number in 1 dimension, 1, 2, 3, 4, minus 1, minus 2, minus 3, minus 4. This is a number in 2 dimensions. That is why we call it as an ordered pair of 2 numbers, right? So for example, I can write a complex number, ordered pair means the first is the real part of the complex number and the second is the, for example, if I have a complex number, let me call it as a Z. It is, let's say, 1 plus 3 iota. You can see that you can write it as an ordered pair like 1 and 3. Right? It means this is the real part, this is the complex part. In ordered pair, whenever I have something at the first place, it will be the real part contribution, and the second is the imaginary part contribution. So if you can write iota, iota has no real part and it has only the imaginary part. So in general, I can write an ordered pair to be the real of Z and imaginary of Z, right? Perfect. Now, if instead of these numbers, I have variables, then this complex number becomes a complex variable, right? For example, Z is equal to x plus iota y. This x can be any number, y can be any number on a complex plane from minus infinity to plus infinity, both in x and y direction. So it means I can plot any point. The only way is I write x over here, and then instead of a y on this Euclidean plane, I can write iota y. It means I can define a kind of a vector, like a vector in vector spaces. I can write x plus iota y, right? Z from here. This point will be x, y, right? So I can write, okay, let me write it as, this is z, and I can write z as x and y. Suppose I add two complex numbers. What happens then? What do you think? Suppose I have two complex numbers. Let's say z1 is x1, y1, z2 is x2, y2. Exactly. So you can write it as z is equal to, let's say you can write z1 plus z2. It means real part is added to real part, x1 plus x2 and y1 plus y2. Exactly like the addition of a vector in Euclidean space. Real component, these are added component by component, right? So if I have two complex z1, let's say I'm drawing a vector just for my convenience, you know, there is no problem with it. So I can write z2, it means I can always find z1 plus z2. Order doesn't matter in the addition, right? Because it is as good as z2 plus z1. So if you just look at this one, then real of z is the real of z1 plus real of z2, just like the vector addition along with its components. Similarly with the y1 and y2. It's perfect. Any question?
Yes.
Please.
Sir, how, if this is, we're looking at complex numbers, right? So how is this different from vectors at all?
From vectors at all?
Yes.
Okay. I'll just give me 1 minute. I defined one operation which tells you why it is different from the vectors. Here, this is like just like the ordinary vectors in the Euclidean space, x, with this condition that one of the axes is an imaginary axis, right? So addition is there, no problem. How about multiplication then? That matters, right? The multiplication will distinguish you from this vectors and the complex numbers. I'll come to this point. I'll prove it that vector distinguish this thing, right? Okay, so before that, you know that triangular inequalities, they will hold, definitely. Why? Because I can always write z1 plus z2 mod is always less than equal to the z1 mod plus z2 mod. Similarly, from this I can write z1 is equal to z1 minus z2 plus z2. I can just add and subtract a complex number, there is no problem, because I have just added 0. So now if I take the complex conjugate, if I take the modulus, I can write z1 mod, and from this identity I can say that it is less than equal to the mod of individual functions. Do you agree to this point? Or you can say that z1 minus z2 modulus is less than equal to z1 minus z2 mod. It's fine, right? So from this, we just use this one, that the modulus of the sum of the two complex numbers is less than equal to their individual modulus, and then using that we can prove this thing, right? I'll come to what do we mean by the conjugate, because I have to define the, first of all, the multiplicative inverse. Once I define the multiplicative inverse, then I'll define the conjugate. Wahi wala, exactly. Okay, so to answer your question, what happens if we multiply the two complex numbers? So if I multiply just z1, z2, you can write it as x1, y1, x2, y2. Always remember that whenever we multiply two imaginary parts in the ordered parameter, we have to add a minus sign, an extra minus sign, right? So you can write it as x1 with x2, y1 with y2, but as it has an iota in it, right? It's just, you can just write it like this one if you like, x1 plus iota, y1, x2 plus iota y2. You can just multiply x1 with x2. At least for your understanding, once in your life you can write it like this one and try to grasp the idea of the ordered pair then, and in future you can just use that. And then you can write it as x1, y2 plus y1, x2. It's fine. You can see this distinguish the vector multiplication. It's perfectly fine. So this multiplication distinguish the complex plane, the complex variables from the R2, from the vectors in the Euclidean plane. Okay, so by the way, once we have the multiplication, it means we can use different laws of multiplication. For example, you can see that these two are the variables, of course not operators which Hassan said. Therefore, you can just write it equally good as x2, x1 minus y2, y1, because the product of these numbers are the variables, doesn't matter. 2, 3, 3, 2, they are the same. Similarly, y2, x1 plus x2, y1. You can write it as, this is nothing but this is z2, z1. It means that is commutative. The product of the two complex numbers is commutative. And then I can write z1, z2 and z3. It doesn't matter if I multiply z2 and z3 first and then multiply the answer with z1, or I can do it like this one. Right? So what is this property? So this is commutative, this is associative. And then of course if you have a complex number that you have to distribute, let me write it as z2 and z3 to two complex numbers, it means you add the two complex numbers first, they will add component by component, real component and the imaginary components, and then if you multiply them with the ordered pair of the complex number, the result is the same as z1 z2 plus z1 z3. This is just the basic knowledge of the complex number. So this is just the distributive property, right? So these are the properties of the complex numbers. I will use them quite frequently in this course. Whenever I have complex numbers, I have to switch them. I'll definitely use. I will have these properties in my mind always, but I'll keep you reminding whenever they will come in use in the course. So any comment, question? I used to probe all the time, you know. This is my bad habit. Please.
At first you gave us this analogy with vectors that complex numbers we could. At first you gave us this analogy with vectors, we could like display complex numbers as vectors, and then you defined this multiplication function, right? And it's very different from vector multiplication and stuff like that, right? Very different. So can we even call these vectors, or what would be the term we use for complex numbers?
Well, if your inner product rule is that of complex conjugation, then you can.
Yes.
Okay.
Yeah, exactly.
As you learned in Hilbert's messes, you have to have a way of getting a number from a vector and the dual. So the dual here
Is that
is your complex, is your
conjugate?
conjugate.
I'm coming to this
Okay,
point.
okay.
Sir, I'm just coming to this point, because 1 over z is the multiplicative inverse of z. So what is the inverse? When you multiply something with its inverse, the answer should be equal to 1. So it means I can say that 1 over z is just the multiplicative inverse of z. This is the, as per Westoff said, that this is multiplicative inverse. So can I write it in some better form? Because I have a complex number downstairs. Yes, there is a way to write it. You can just multiply with its complex conjugate upstairs and downstairs. Right? Exactly. So you can write it as 1 over z. You can just write it as, you can multiply with z star and then write z and z star. So you can see that z star has some component 1 over z squared downstairs. And what is z squared? Z squared is x with x, x squared, y with y, y squared. But it's a modulus. In the modulus, you have, in this star operation, you have to change every iota to minus iota. So if you ask me how I can write this z star in the complex plane, in the ordered pair, then the idea is very simple to write it. You just have to add a minus sign with the imaginary part. So you can say z star, if z is your xy, then your z star is, x minus y, right? Perfect. So now if you write modulus of z squared, then this is x squared plus y squared. So this is kind of a radius of a circle if x and y lies in a complex plane. So the modulus of this z is the radius of the circle in that complex plane. I'll come to this point if this z extends to infinity in this lecture, in the second half of this lecture. And one last thing which I would like to mention is, because you see that if I plot them on a xy axis, for example, if this is x plus iota y, or you can say this is x iota y, then beneath this is x minus iota y, if this is x plus iota y, right? Because this is iota y, this is x, right? So if you draw angles, for example, in this way, you will see that in this case you have the angles in this way, in the first and the fourth quadrant, right? On this side only, because x remains positive in both cases, only y changes the sign. Okay, so, and all this conjugate properties that you take a conjugate, if you take a sum and then take a conjugate, then this complex conjugate distributed on the two. For example, if you have two complex numbers, these are very trivial properties to prove, and this is equal to z1 star plus z2 star. This is one property. If you have the product of the two, for example, z1, z2 whole star, then you can write it as z, you can take first their conjugate, multiply them, or you can multiply them first and then take the conjugate. These two things are the same. And of course, there is no problem if I even switch the two, because they are, in any case, they are the commutative. Can you tell me what happens to this thing? Anyone? Anyone? Okay, exactly, sure. Very good. So it is z1, z2. I can write it as z1 star, z2 star. There is no problem. I can just switch the two. So this can be written as z1 star in one bracket, z2 star in the second. So this is equal to the z1 mod squared and z2 mod squared. So this is equal to z1 z2 mod squared. Right, Amna? Now it's correct. Okay, so you can see that you multiply the two, take a mod square is equal to the multiplication of the individual modulus squares. Till now everything is very simple, except just one thing which is new compared to this intermediate books, which is the ordered pair. Rest of the process is exactly the same as we studied in our college life. Now let me, because this is a very simple, and we know a lot about the trigonometry, and we have to remember a lot of trigonometric formulas all the time. For example, if you remember sine square theta plus cosine square theta for every theta, you can say is 1. Then you can derive many formulas from this, 1 plus tangent squared, 1 plus cotangent squared, depending upon that. But in the complex number, there is a better way to obtain different, you can always write if, for example, you have cosine of A plus B. We know that it's the multiplication of the cosine minus some sines, right? From the complex numbers, representing them in the polar coordinates, you can easily get these formulas. So I'll briefly discuss them and then come to the main topic of this lecture. So let me tell you the polar representation, and here I'll talk about the roots of a complex polynomial equation. Let's talk about the polar representation. You know that you can write R in term of X in term of a length of a radius and the angle it makes with, suppose, x-axis, you can say. So you can, X is just the projection of that on the x-axis. Y component is just the projection on the y, but you have to change angle from theta to 90 minus theta, right? So you can write X is equal to, if I write it X is equal to R cosine theta, then my Y is R sine theta, right? So I can write X mod square plus Y mod squared is equal to R square. You see, this is basically Z modulus square, right? You can always make a change of variables, which I'll do in after some time, For example, if I divide this equation with R squared, then what happens? I have X squared over R squared plus Y squared over R squared. This is equal to 1. It means I have a circle of a unit radius. Why not I define this as a new variable, let's say rho 1, and I can define this variable as a rho 2 or capital X1, capital X2, whatever you say. So I can write rho 1 squared plus rho 2 squared is equal to 1. And remember, this is just this Z modulus square. So I have basically drawn this complex number on the unit circle now. With this change, that my X over R is a new variable. So whenever we do physics, we always prefer to work with the dimensionless quantities, so that in between the mathematical calculations that is too rigorous, especially the series calculation, For example, you have sine theta, sine of A. You necessarily mention that A has no dimension, because if you expand it in the series, then higher terms have high dimensions. So that is why we always prefer to work in the coordinate systems or with the variables, you can say, that are dimensionless. And I'll use this concept, And similarly, you can write this, if you write Z, which is your X plus iota Y, then you can write it as R, and this, I can write cosine theta as C theta, just to save my time, and sine theta as iota S theta. So this is equal to R e to the power iota theta. This is the Euler expansion of R e to the power iota theta, which is R cosine theta plus iota R sine theta. So, any question? It's fine? Okay. What happens if I take the conjugate of it? I mean, what happens if, so we have found the R, how we can find theta? We know that in ordinary polar coordinates in the vector space, theta is the tangent inverse. But here we write it, instead of a tangent inverse, we write it in the form of an argument of z. I'll come to this point, as I said when I discussed the branch cut. You know, for example, just to give you an idea that, okay, theta is just tangent inverse y over x. If you are given to calculate y is 1, x is 1, you were asked to calculate tangent inverse of 1. For example, you have pi over 4, because it is some point where sine and cosine are equal, and that is a 45-degree angle. And if I ask you to calculate -1 minus iota, suppose you don't know this point, again you have pi by 4. But in your mind you have x is negative, y is negative, so it is in the third quadrant. So instead of a theta, we always use argument of z. That is not always equal to tangent inverse. So we can use small, now there is a distinction between the two. Argument of z, that can be written as, this corresponds to theta, by the way. This I will define with the theta. And now there is a capital A value also. We can, what is the capital argument with capital A? This is a principal value with the preferred choice from minus pi to pi. And I'll come to this point, what is the principal value? This is a standard choice that if I limit my theta from minus pi to pi, then instead of argument of z, I can write argument of z, right? And the small argument of z is multi-valued. It can be written from capital argument of z plus, I guess, 2k pi. Why I have written 2k pi? So that I can take k is equal to 0 plus minus 1 plus minus 2 up to so on. Because we know that if I have sine and cosines, then after every 2 pi, we come to the same point after 2 pi rotations. So if you ask me the range of this one, I say that whenever I calculate minus pi is less than theta is less than pi. So if you calculate it in the form of the argument, this is pi by 4, this is minus 3 pi by 4. Because it is in the third quadrant. In the third quadrant, you have both x and y negative. So you see, I have limited this with capital argument of z from minus pi to pi, because minus 3 pi by 4 lies from is less than minus pi to the pi by 4. Perfect. Any question? This we use quite frequently in this course. So you see, this argument is multi-valued. For every theta, if you change 2k pi, you will get the same argument of z. You can get the same answers. Yes, please.
Sir, about the small argument you just mentioned that it would be theta is equal to minus 3 by 4 pi.
The capital, this one.
Achha,
This one. I said that its range is, you can say I have chosen a standard range. And just to define my standard, instead of a small a, I wrote it as a capital A.
Achha, okay.
Right?
So what's the motivation behind this? Why we have?
You see that we know that because this is multi-valued function. Out of these multi-valued, I have made a special choice, and this will come to effect when I calculate log of z.
Okay.
I have a log of r plus log of e to the power iota theta, and now this log becomes a multi-valued. And then you see I'll define the branch cuts, as I said in the Jordan lemma. So the problem is that this is not unique. This is unique from minus pi to pi.
Okay.
Standard choice.
But if I choose the argument from 0 to 2 pi, what will make a difference?
No, minus pi to pi is just to, as I told you, this one, to mention my quadrant also. Range is,
It won't make
any difference as far as for 2 pi, yeah. But I said that just to make the choice of a quadrant, you can take minus pi to pi. Otherwise, the range is 2 pi.
0 to 2 pi is also good.
Okay.
And, minus pi by 4,
Four to-
pi by 4 to 3 pi by 4 is also good.
Ah, okay. Thank
But
you.
you don't want to do that.
Okay. Thank you. So the difference is always 2 pi, right? The whole 360. Okay. Thank you for the comments. So what about this thing, e to the power iota theta modulus? Because e to the power iota theta is this part. So this is 1. What about e to the power iota theta star?
1.
E to the power, every iota will be changed to minus iota and theta is real. So you can see that if I have an argument of z here, then argument of z star is as good as argument of z with negative sign, because you can always write it as e to the power iota minus theta. If this is the argument of z, this is minus argument of the z. Okay, so one last point about these identities, and then, okay, so what happens if I write e to the power iota, you remember e to the power iota theta 1, e to the power iota theta 2. This is just iota theta 1 plus theta 2. By the way, this is a very, very powerful expression. You can derive the trigonometric formula from the sum to the product. You will see. You can write it as c cosine theta 1 plus theta 2, and then in ordered pair form you can write it as sine of theta 1 plus theta 2. You can write the product of the two. Let me write it first. So I can write cosine theta 1, sine theta 1, and then cosine theta 2 and sine theta 2. So you can just multiply the two, and remember you have to gather real as a first number in the ordered pair and imaginary as the second number. So you can write cosine theta 1, cosine theta 2 minus, and I told you that whenever you multiply the two complex you have to add a minus sign in the ordered pair, sine theta 1, sine theta 2. And similarly you can write cos theta 1, sine theta 2 plus sine theta 1, cosine theta 2. It's very simple, right? Now you see, all the trigonometric formulas that you know, you can just find them from this Euler expansion. So you can have cosine, I can write theta 1 plus theta 2 as I told you that I will use this shorthand notation to save my time. C theta 1 plus theta 2 is equal to C theta 1, C theta 2 minus S theta 1, S theta 2. By the way, there is a way to check it, you know. For example, if theta 1 and theta 2 both are pi by 4, right? So what you have, cosine of pi by 4 plus pi by 4 is pi over 2, and cosine when on the y-axis is 0, right? And similarly, if you do it over here, this is same, sine and cosine are equal at pi by 2, so this formula is correct. It's perfectly, you can quickly check it. And similarly, you can check it for any value of theta. Similarly, you can write sine theta 1 plus theta 2 as this part. So C theta 1 S theta 2 minus S theta 1 C theta 2 plus, exactly, thank you. Very good. Similarly, if you use minus over here, you can see that this will change sign, and perhaps this will also change sign. You have to check it out. So you see, as I told you, that all your trigonometric formulas you can easily derive. How about e to the power n theta? How about e to the power iota theta n? You can always write it as e to the power iota theta to the power n, right? So you can write it as c theta plus, by the way, I can also write it as ordered pair, but n. The famous De Moivre's theorem, right? So you can always write c theta plus iota s theta to the power n is right c n theta plus iota s n theta. C n theta means cosine n theta, s n theta for iota sine. Sine n theta. I apologize for these notations, but you know, let me put this thing, not this one, just to distinguish it from the series Cn and Sn. So it is the argument. So just to save time, yes. Right, and then you can do anything you like. For example, you can calculate square, you can calculate cube, you can calculate anything, provided you know the binomial theorem, right? So if you know the binomial theorem, take it as a one quantity, take it as an other quantity, divide, let's suppose you can just write, you can just expand it, and you can calculate every single thing that you write. I mean, just you have, or you can just multiply them with the concept of the ordered pair multiplication. If you have to calculate square, cube, fourth power. But if you have to calculate larger power, then that's a problematic, and then you have to make some expansion rules for that. So, नहीं, हाँ आसान है. अच्छा चलें, एक आखिरी चीज थी जो, चलें इसके लिए करके देखें. Okay, let's do it like this one. C theta plus iota S theta cube. This is, in our definition, it is cos 3 theta plus iota sine 3 theta. I remembered it, in some hope by heart, that this is equal to cos cube theta minus 3 cos theta sine square theta. Why minus? Because when I squared it, I have iota squared also. And then I have plus 3 iota s theta cos square theta, and then minus s theta cube with iota, right? Because iota cube is minus iota, because you can write iota cube as iota squared into iota. So iota squared is always equal to minus 1. So now you can just compare the real and imaginary part on the two sides, and you will get the formula for this in a very, very simple way. So you can see this part of expressing this complex number in the polar coordinates. You can get all your trigonometric formulas that you learned in your school, college life, high school. Okay, so suppose I have two complex numbers, and I can write them like this thing. I don't want to talk about the polynomials right now, but that is a polynomial in itself. If I write it like equal to 0 or something like, suppose I have a Zn is equal to some W. W is a complex number, Z is a complex number. So Z is the nth root of W. I'll give you an example how to calculate the nth root of this one. So let's go to the polar coordinates. You can write Z is equal to R e to the power iota theta, and you can write W as, and you can always write this as, this is a polynomial of Zn minus W, right? It's this kind of a polynomial, then I will write. So in W I can write rho, and I can choose its angle to be different, iota phi. You can just substitute it over here. What you get? R to the power n e to the power iota n theta is equal to rho e to the power iota phi. It's correct? Now what happens next? So this implies if I compare them, I can say that Rn is equal to rho, right? So I can write R as rho to the power 1 over n, right? And how about theta then? Huh? Not only phi by n, why? N theta is equal to what? Why phi? Why only phi?
Plus 2n pi.
Exactly, this whole range, So I can write it as phi, I can write it phi plus 2k pi. Or I can write theta is equal to phi over n plus 2k pi over n. So you see, you have written z coordinates in terms of the w coordinates. Both are the complex number. We can understand it with an example, For example, this is now the nth root of it. If I ask you to calculate the cube root of, let's say, 1 plus iota, this is the simplest complex number, 1 plus iota. If I ask you to calculate its cube, how you can calculate that? What is R? R is, very good. So R is x squared plus y squared, the modulus of x squared plus modulus of y squared. So this is equal to square root of 2. Very good. How about theta? 45 exactly, because both are in the first quadrant. Both are in the first quadrant, so theta is my, I can say that this is pi over 4. So this implies is I can write 1 plus iota as just only 1 plus iota. I haven't considered the power yet. So I can write under root 2 e to the power iota pi over 4. Now what happens if you calculate the cube root? Then how you can write this one then? Any comment? Any? Okay, so we know that R is rho to the power 1 over n. So you have written under root 2 and you have to divide it with 3, right? N is equal to 3. So you can do it like, so, oh sorry, this is power. So this implies my R is under root 2 to the power 1 over 3, right? So what is this one? 2 to the power 1 over 6. And why not I choose only 1? I mean, because k is 0, 1, 2, 3, 4 up to so on n minus 1 you have. If you have n values, then k, if you choose k from 0, then you have n minus 1. And then you can write theta, let's say, because you can take k is equal to 0, k is equal to 1, k is equal to 2. Because you have to have 3 roots, right? And they are different. For the first part, you can write one thing. For the second, you can write second. And for the third, for k is equal to 0, this is nothing but this is, okay, I think I should write it as phi, sorry, right? Yes, it's phi, and this is my rho, sorry, because one z and w, they are mapped, right? So theta is my, you know, so this is pi over 12 for k is equal to 0. And similarly, you can write k is equal to 1, 2, 3. And then you can plot it on a circle, right? One of the radius you have under root 2 e to the power iota pi by 4. For k is equal to 0, you have cube root as 1 over 12. And when you put k is equal to 1, you can calculate nu theta, plot it on the circle, and then you can do it for the third one, right? So you can plot it on a circle. It's very easy to prove. I mean, you can just plot, and you can have 1 over here, let's suppose pi over 12, and then you have, let's say 3 pi over 12, and then you have over here. So you can plot that on a unit circle. I'll plot these in details, you know, in my from now on, from the second half of the lecture.
K is always n minus 1?
Yes, because you know, okay, so you have considered k from 0 to n minus 1. So there are n values, because 0 is included, right? If you start from 1, then you have to n, you have to go till n, because that's a 2n pi. Okay, so this is all about the complex numbers, their roots, you know, and in this way you can find any root of any equation in the polynomial, you know, in the complex, for the complex numbers.
And sine instead of all this?
Yes, because cosine and sine give you the angle, you know, theta is the argument of that, which is tangent inverse. I used y is equal to 1, the number that comes with iota, x is 1, that number is real. So that is pi over 4. So I have expressed it in terms of, by expressing it in terms of r and theta, I have written rho in terms of r and theta in terms of phi. Zn is the nth root of w. So that is why I have found the coordinates of the w, and then corresponding the coordinates of the variables of the z, rather, r and theta. By the way, there is a one, till now, you know, everything is very simple, but there is a very important difference when you come to the complex functions. You know, Pravesh Sahab in his lecture told you about the function. You have an input, you feed to some machine, it will give you an output. For the real function, the input is real and the output is real. But for the complex function, things are very different. Input is complex, output is complex. And that is not only any complex, it is a specific combination of complex numbers. For example, if I define f of z as a function of, because z is x plus iota y, then it is independent from the f of z star, because z star is independent of z, because that is x minus iota y. And you will see that it has a very deep relation with the analytic or holomorphic functions. You will see that if f of z is an analytic function of z, f of z star is not the analytic function of z. But before that, before talking about the analytic function, there is one another problem for the complex numbers or the complex variables. For ordinary functions, if x and y are independent, there is no need to write a specific combination of x and y. You can write xy, you can write x squared plus y. But for the f of z, this z is a specific combination of x plus iota y. Right? So x and y are independent. For the ordinary functions, you can say that x runs from minus infinity to infinity, y runs from minus infinity to infinity. So along the x-axis, either you can go from minus infinity to infinite. Along the y-axis, you can go from minus infinite to infinite. But for the complex number, these are not only the two directions. There are infinitely many ways to go to the infinity along different rays. You know, I can do it like this one, whatever you like, man. You can go to infinity in any, sorry, all these goes from this center. So you have a ring of, whole ring of infinitely many points. It means in the complex plane, you can go to till infinity. So is there a way to map these infinities and have a good understanding of that? The idea is just like the ordinary non-infinite plane. How you have, suppose this is a ring and this is finite. बिल्कुल घर की चपाती की तरह. You can just roll it from every side, compactify it. It means you can make a sphere. This way of compactification is known as a stereographic projection, and it has important relation with the manifold. I'm sure Pravesa will talk about some of the geodesic distance, but I'll calculate the distance on this complex plane, right? So my idea is, suppose I have a round mat in this room. It's an xy plane. When I say xy plane is x iota y plane, I can just compactify it, roll it in such a way that it becomes a sphere. And on a sphere, I have something. Let me draw this. My drawing is not that good, but I'll try to make it bigger and keep it for the rest of lecture. And you know, I told you an idea of x squared plus y squared is equal to r squared. You can just choose a right coordinate. You can draw it on a unit sphere. It means I can compactify and draw it on a unit sphere. So in this way, I have just trying to map this infinity on some kind of a surface, right? So I can say that, okay, you have a not bad sphere, right? And here you have an equator. Above the equator, let me draw this thing, and then this thing, and then this axis, right? This is my x, this is my y. I don't want to call it as a z because z is reserved for x plus iota y. So this is the third axis.
Could I like ask what you're doing exactly is xy plane ke upar, you're taking all the points and then mapping them.
Exactly. I'm trying to explain how you can map the points.
So
Exactly.
Would that be like 4 dimensions?
4 dimensions? Yes.
अच्छा, so 4th dimension is
मैं देख ही नहीं सकता, मैं तो 2 draw कर सकता हूँ, 3 भी नहीं कर सकता. So this is kind of a hollow sphere. I'll tell you how mapping exactly work. Just imagine it in a 2-dimension x and y, right? So you can draw a plane, complex plane over here on the equator, right? This is my complex plane. I call it as my C plane. Right, on this complex plane you have y and x. This plane is flat if you cut it from the equator, you have a rounded sphere. If you cut it with a knife like this one, this complex plane is cutting this sphere in 2 semi-spheres, right? Northern hemisphere, because upstairs is north, if I have an equator on east-west, and here is the south. right? So now if you draw any line from this point, by the way, let me tell you first this sphere, because this sphere satisfied x squared plus y squared is equal to 1. If I consider this unit as a unit sphere, by the way, this unit sphere is known as we call it as a Riemann surface or Riemann sphere, whatever you call it. On this Riemann sphere, you will see I'll map the point, complex planes point on this sphere. Now, if I draw a line from a north pole, my point is it will definitely hit the complex plane at some point, right? For every z less than infinite, there is no problem. For every z, if I have a set of complex number, which is less than infinity, I call it as a complex plane. If I include infinity, it is known as an extended complex plane. So there is no problem with that. Now imagine this is a stick. And by the way, this is cutting the plane at this point, right? Sphere at this point is exactly what you see, some mapping. So the point on the sphere is mapped to the complex plane whenever I draw any line from this one. And what is this sphere? This sphere is z mod squared is equal to 1. Is a unit circle, right? The equator is a unit circle. So if you just know, change the angle of this ray, you can see that this point is moving far and far. It means if I want to bring this point exactly at the north pole, I might be hitting this plane at an infinity. So in this way, I told you that from this concept of finite compactification, you map the point of a complex plane on this Riemann surface, right? So no, it means I have to choose some coordinates. I should draw this line over here, so that it cut the sphere at this point. So I have to choose the coordinates in the spherical, in my new coordinates for this unit sphere. Yes, please.
What happens inside the points inside this?
Thank you very much for asking this question. Otherwise, I completely forget that. Okay, so this is not necessarily on this side of an axis. This can also go on this side of this axis, because you can also draw an array on this side. So you can go from either side of the plane to the north pole. What happens if your point lies on the inside this sphere, you can say rather. All these points are mapped to the southern hemisphere or the south pole, because z mod is less than 1, right? So there is no problem. We have mapped every point that lies inside this surface, every point that lies outside this surface on this Riemann sphere, right? Clear? Now I have to calculate the coordinates of, because x and y are my coordinates, are the coordinates of my z plane. I have folded this compactified this complex plane rather in the form of a Riemann sphere, and I have its coordinates also. So how we can find a relationship between the coordinates of the Riemann sphere and the coordinates of the complex z plane? I will find these relations. And what is the next task is to find the distance between 2 points on this complex plane, and that you will be surprised to see. Mark my words. So how you can do it? Of course, you can make an angle with the longitude and latitude, polar angle and the azimuthal angle. Polar angle runs from 0 to pi, azimuthal angle runs from 0 to 2 pi. So you know one is you call as a theta, other you call it as a phi. As I said, it's not my only choice to have one, but I can always choose a set of coordinates in which I can divide it for any finite r, and on the right hand side of the sphere I have 1. So it means I can write rho 1. I can write rho 1 as the coordinates of this Riemann sphere. I can then call it as a rho 1 and then rho 2 on this axis and then rho 3 on this axis, right? So rho 1 is sine theta cosine phi, just like x. Rho 2 is sine theta sine phi, and rho 3 is cosine theta. But there is a constraint, only one constraint, and that is rho 1 squared plus rho 2 squared plus rho 3 squared is equal to 1. Why? Because you can just add these three, you will get the 1. or you have the radius of this unit, the radius of this Riemann surface to be the 1. So out of these three, only two are independent.
Doesn't make any difference, but I think theta and phi have to be switched around. So the normal way is to say rho 1 is cosine theta, sine phi.
No, sine theta cos phi, because the angle is with z. Azimuthal angle is with z, so it's a cos theta.
So can you draw that theta and phi?
If this is my z axis, this is my theta. So you can say that this is cos theta, this is sine theta, and then sine theta will
Phi.
No, I'm saying that this is my r sine theta, and then this will go on this side and this side. So sine theta cos phi, sine theta sine phi cos theta. I guess I have written it correctly, is it?
Phi. Phi is the azimuth.
Yeah,
right?
this is phi, right? Yes. So phi is actually the motion of one of the component of r sine theta.
Okay.
But this is, in a fancy language, you can call it as angle with co-latitude and longitude. So I don't want to convey. Yeah, no problems. No. I always make mistakes. So.
Sir, अंदर वाले the points include करें तो फिर तो north pole.
No, if you include all these points that lies inside, they will map to south pole. What is the difference between north and south pole? The coordinate distance, you will see 2. It will naturally come out to be 2 because origin is over here. There is no way to map this to inside because at maximum, if you soon you touch this point, you come inside, you have to map them to the south pole. Just think about it, and then tomorrow I can also give it more intuitive than if you, but spare some time to think about it then. Okay, so how I can express this rho 1, rho 2, rho 3 in terms of x and y? Because as you said, there is a mapping. So suppose I have a complex number of rho 1 plus iota 2, and by putting their expressions, I can get x plus iota y. It means I have mapped the point of the Riemann sphere to the point on the complex plane. So my whole effort is to go for this one. There is only one assignment for you in this whole thing that you have to do. I have done one assignment. I can give you these handouts, so there is no problem at all. So you see that this is my y, and this is my, let's say, rho 2, this is my rho 3, and this is my 1 minus rho 3. So by the similarity of triangles, the ratio, this ratio, which is to the ratio of this to this, is always equal, right? So I can say that, I have to write it correctly. So I have to say, in any case you can choose this, 1 minus rho 3 to 1 is equal to rho 2 over y. So ratio of this to this is equal to ratio of this to 1. Okay, so you can write, so this implies that you can write rho 2 is equal to y over 1 minus rho 3. Similarly, if you draw it on an x plane, there is no problem, y is replaced with x. So I can write rho 1 is equal to x over 1 minus rho 3. But there is a constraint. Rho 1 square, rho 2 square, rho 3 square is equal to 1.
Rho 2 y multiplied by 1 minus rho 3 y अगर डिवाइड हो रहा है हम कहते मल्टीप्लाई में
ओह, कुछ गलत लिख दिया मैंने.
So it implies
ओह, मैंने कुछ गलत लिख दिया. इसको उलट करना चाहिए था मुझे. I have to write it correctly. So 1 minus rho 3 over 1 is equal to rho 2 over y. This is fine, right?
after आपने लिखा rho 2 is equal to
Cross
y
multiplies.
Oh, sorry. You are right. So you want to say me that y is equal to, okay, this is wrong. So y is equal to rho 2 over 1, or x is equal to rho 1 over 1 minus. Now it's correct? Okay, thank you. Now I have to write it in terms of a, can you calculate, okay, I have found these x and y, they are of the complex plane, right? These are the coordinates of a Riemann surface. Can you express one in the other way? I mean, can you find rho 1 and rho 2 in terms of x, y. This is an exercise and I'll do it in this class, and next thing you have to do by yourself. So one thing I'll do and the rest of the part you have to do. But before that, let me express them in terms of the angles. And then I can write x is equal to, x is rho 1 is what? Sine theta cosine phi over 1 minus cosine theta. So this is 1 minus cosine theta is 2 cosine squared theta by 2, right? Or sine squared theta by 2. Okay, let me write it. 2 sine theta by 2, because this will make it more intuitive. Cosine theta by 2, let me erase it. So x is, so this is 2 times sine theta by 2 cosine theta by 2, and then cosine phi, I don't want to change it to half angle, and this is 2 sine square theta by 2. It's fine, I guess. So I can cancel this to one of the sines. So this is nothing but this is cotangent theta by 2 cos phi. Now this part has no problem because this has sine theta sine phi. Except sine phi, this half angle part will remain same. So you have y is equal to cotangent theta by 2 sine phi. And you see, if you write x plus iota y, then you have a kind of a phase with it. Cotangent theta by 2 and then e to the power iota phi from x plus iota y. So that is fine. I guess that is correct. Okay, so I have to erase it. You have to keep it in mind because I have it on my paper, so there is no problem. Everything is fine till this point, right?
कॉम्प्लेक्स टाइम में हम इंफिनिटी लेते हैं उसको हम छुपा सकते हैं
हाँ.
इस तरीके से.
Okay, exactly. You can just map it. Infinite point is on the north pole.
सर जिस तरह हमने क्वांटम फील्ड की लिमिट किया था ये
It's a conformal mapping, and then you have this. By the way, this stereographic projection might seems to be a very new name, but exactly you have written these kind of coordinates for the spins in quantum mechanics on a block sphere.
yes sir blocks.
Exactly, you have written a sine theta cos phi, sine theta sine phi, provided you have chosen z axis as your axis of quantization, and then on that axis you have a projection which is cosine theta, right?
Yes.
So this is, even in the conformal field theories you use this one, stereographic projections. So it has lot of applications in physics. F of z, no, because f of z is x plus iota, but that I called as a third axis only. Because it's in any case a plane. Third axis is my own choice. I don't have a sum of x plus iota by that gives me the vertical axis. Absolutely not. Because we know that for the vectors, if you multiply two vectors in a cross product, then you get the third. There is no way for this one. So what I can do is, let me calculate, imagine if you have rho 1 and if you just calculate x rho 1 plus iota rho 2 over 1 minus rho 3, what you will get? X plus iota y. But let me calculate first rho 1, rho 2 and rho 3 in terms of x and y. You know my constraint is what? Constraint is rho 1 squared plus rho 2 squared plus rho 3 squared is 1. Let me get rid of rho 3 on this side. So I can just write it as, so this is as good as, so let me save some time, and I can write it as 1 minus rho 3, which is nothing but this is 1 minus rho 3 into 1 plus rho 3. This one. Now you have rho 1. Rho 1 is x squared into 1 minus rho 3 squared. So you can write x squared plus y squared into 1 minus rho 3 whole squared, right? Because this factor is common when I multiply it with x and y. So I can write it as 1 minus rho 3 and then I have 1 plus rho 3. So you can just cancel the 2 and then you can calculate rho 3. Now your rho 3 is what? Okay, let me do it. X squared plus y squared minus 1 is equal to x squared plus y squared plus 1 into rho 3, right? I multiplied with negative sign, took it on this side, and then rho 3 is common. So this implies is my rho 3 is x squared plus y squared minus 1 over x squared plus y squared plus 1. Now you will see, even if you take z to be infinity, you will get something very physical from this one. What is x squared plus y squared in terms of z? So I can write it as z squared minus 1, and this is z squared plus 1. Now I have rho 3. If I have rho 3, I can calculate 1 minus rho 3. And from 1 minus rho 3, then I can calculate rho 1 in terms of x. So that's not a problem, right? Can you do it? So my answer for this is my rho 1 is 2x over, I guess, x squared. Let me check so that I don't want to. This is a small assignment that you can do now. I have written it somewhere. Okay. So 2x over x squared plus y squared plus 1. And then rho 2 is 2y over x squared plus y squared plus 1. There's no problem. You can see that if you have 1 minus this thing, x squared, y squared will cancel, this minus will change a sign, then you have a factor of 2. It's no problem. So from 1 minus rho 3, you have a factor of 2 over x squared plus y squared plus z squared. And then you can also write them in terms of, you know what is z? Z plus z star over 2 is your x. Because z star has minus iota by, they will cancel, and then similarly you have z minus z star over 2 iota as y. So you can write them in terms of your complex. Remember, z is what? Z is a complex plane. So you have written rho 1, rho 2, rho 3 in terms of your complex plane z. Fine? Any question? Okay, so how if I can calculate rho 1 plus iota rho 2 over 1 minus rho 3? You can just substitute this over here. You have 2x, 2 you can take common, and then you have x plus iota y, and then if you calculate 1 minus rho 3, then you have a factor of 2 downstairs, and then you can see that it is equal to x plus iota y, which is your z. So you see, this rho 1 plus iota 2, which are the coordinates of the Riemann sphere. When you express them in terms of an xy, that gives you the coordinate of your complex plane z. This way of writing is known as a stereographic projections. The wonderful thing is the distance between the 2 points on this complex plane. How you can calculate it? How you can calculate the distance between 2 points? That is your assignment, and I'll ask you to show it to me tomorrow. I can tell you how you can do it. A little bit simplification that you have to do. I can tell you a simple way to do it, not in terms of a theta and phi, but just in terms of a standard way of doing distance between 2 points. Exactly. You can just do it, calculate it from. I can take 2 points. One is z1, other is z2, and I can just interchange and mix it with rho 1, rho 2, etc., etc. So you can take 2 points, apply the standard distance formula, which is x2 minus x1 squared plus y2 minus y1 squared plus z2 minus z1 squared, the square root of it, just the distance between the 2 points. I used to call it as a caudal distance because these 2 points shouldn't be very far on the curvature. Parvez Saab is an expert, he will talk about it in detail about this caudal distance, But my caudal distance is, I draw a line on a plane. I suppose I have this thing. In ordinary language, you have calculated S is equal to R theta, right? right? But that happens for the small theta. When you have the small distances on this complex plane, on the sphere, they become the great circle and they have the relation with geodesics. I don't know about them. But let me do one thing for you, and that distance is the caudal distance between 2 points in an hollow sphere. If I get answer is equal to 2 from between north to south, it means my formula is perfectly fine, and you will see I'll get it. So I can divide, you can write it as d z1 z2. Your assignment is what I have done is I can tell you, I have written x1, x2, x3 in terms of rho 1, rho 2, rho 3, for example. I have taken the difference, given it to some Mathematica, asked it to simplify and then collected the terms. And this is exactly, younger generation is much better programmer than me, then you can easily do program that, And the answer is the following. Answer is quite interesting. It is 2 times z1 minus z2 over the square root of z1 mod square plus 1 z2 mod square plus 1. One thing is very interesting about this, by the way. Can you notice that? What is most interesting about it? dz2 z1 is equal to, because if you just interchange 1 and 2, you have a modulus eat up all the negative signs. It means this is symmetric. So it doesn't matter in which way you measure the distance, it should be symmetric. It should be symmetric on this caudal distance is symmetric. Now what happens if z1 and z2 are equal? The distance will be 0 if and only if the 2 points are exactly on each other. If and only if z1 is equal to z2. I don't think so by any other mean you can have the distance to be 0. What is the third thing that you can extract from this one? Inequality, triangle inequalities also hold, If you have 3 points, you can calculate the distance from 1 to 3. It is always less than distance from 1 to 2 and then 2 to 3. That's the standard. What happens if you take z2 to infinity? You will see now. One of the point on the complex plane is infinite. If your distance comes out to be finite, then it's perfectly fine mapping. There is no problem. We have compactified it correctly. What happens? Let me take z2 to be infinity and z1 to. I can define z1 to be z because there is no need to write z1 then. Can you simplify it? You can just take z2 to common. z1 over z2 goes to 0 as z2 approaches to infinity. Similarly, you can take z2 and then what is the answer? No, not 2. Why 2? Z2 that you take common from here, we'll cancel with the Z2 that you take common from here. And then this is 2 over square root of Z squared plus 1. That is the caudal distance.
One more interesting thing.
Yes, please.
If you take Z1 is very close to Z2. Why don't you do that?
If I take
Z1 to be very close to
if I take Z2 is equal to Z1 plus some small number you want to say? Okay. Yeah. Then this I have epsilon upstairs, right?
Yes.
And then I have to ignore epsilon squared term over here.
No, you can take Z1 equal to Z2.
Okay. If I take, then I have Z squared down, Z squared plus 1 down, say 2 epsilon over Z squared plus 1.
Yeah, that's right.
That's right, yeah. That's a very, very small distance then.
Okay.
Yeah.
Yes.
And if this epsilon approaches to 0.
You have essentially calculated the metric tensor on the Riemann sphere.
Riemann sphere, exactly. Yeah. You are right.
Exactly,
I got your point. Yeah,
you have metric, 2 points which are infinitesimally separated from each other. The square of the distance is then what you've calculated.
Wow, that's great. This I never knew, Thank you very much.
You know it.
Yeah, okay. No, I never thought. So it means this is something, this constant will be multiplied with the metric that you have.
So you found the
We found that metric, exactly. Thank you very much, sir. Thank you. So what happens if you take now distance between origin and infinity? 2. Why? Because chordal distance between north and south pole is 2. If you take origin in between, downstairs you have 1, upstairs you have 1, you can just add. So this is exactly the chordal distance between north and south pole on this unit sphere.
माइनस इन्फिनिटी से प्लस इन्फिनिटी जो प्लेन पे डिस्टेंस है वो रीमान से
Exactly 2 होगा क्यों बशर provided you an origin at the middle. I have seen some people doing the stereographic projections in some books that they take it to the horizontal, I mean the plane at the south pole, but I never understand that. This I understand very well. By the way, these things are given in different books. For example, I forget to mention that I have chosen 2 books. One is the Arfken and the other is the Rayleigh and Hobson. I'll give you the names of and the copy of those books also. Right? They have the standard. Arfken is slightly difficult for the fresh undergraduate students, but Hobson's book is much easier than that. And then there is a Krasik's book for physics for scientists and engineers that you can also do. Can you calculate this one final thing in terms of angles? This chordal distance in terms of angles. You know Z1, Z2. Easily you can calculate it. You just need to calculate Z1 minus Z2. And what will you get? You know Z1 minus Z2 is what? By the way, suppose you take 2 points same points on the longitude. It means you can just get rid of phi. You can take phi 1 is equal to phi 2 and they are the same, so there is no problem with this one. So I can write it as e to the power iota phi modulus, and then I can write cotangent theta 1 over 2 minus cotangent theta 2 over 2. Because this is a phase, so just get rid of this phase. So I can write it as cosine theta 1 over 2. Let me write theta 1 over 2 as A and theta 2 over 2 as B. So that I can have cosine A over sine A minus cosine B over sine B. And where A is theta 1 over 2 and B is theta 2 over 2. You can just multiply them, apply the formula that you have derived in the first half of this lecture. So this is cosine A sine B minus cosine B sine A over sine A sine B. So you have cos A sine B, and then you have cos B sine A. It means this is sine of A minus B. So it doesn't matter. I have a modulus in any case, so no problem. So you can just write it as sine of B minus A over sine A sine B. Let me calculate the chordal distance, the denominator of this one. You remember what is the denominator? Z1 squared plus 1, Z2 squared plus 1. So you have 1 plus cotangent square A, which is equal to cosecant squared A. And then you have, this is just your Z1 mod, this is your Z1 mod squared plus 1. And similarly, you have Z2 mod squared plus 1, right? And then you can do, that becomes 1 plus, this is just cosecant squared and B, right? So now you have to just substitute it over here, so I can just, so let me write the chordal distance in terms of these angles, So I can write it as sine of B minus A is my sine. there is a factor of 2 also. This is very important factor because after all it is a distance between north and south pole. So this is sine of theta 2 minus theta 1 over 2, and then I have, right, I have cosecant A, cosecant B, because 1 over sine A is just cosecant A. And so similarly I have cosecant B, and from the denominator I have cosecant A and I have cosecant B. So you can just cancel them, and then you have 2 times sine delta theta over 2. Remember, your theta is the angular distance, and if you take a small theta, what happens? The sine theta for small theta becomes, so for small delta theta, if delta theta is small, delta theta 2 is even further smaller. So you can write sine delta theta over 2 as delta theta over 2, and then this distance becomes 2 into delta theta over 2, which is equal to, I guess this is known as a geodesic distance. So this is known as this is the shortest distance on this Riemann sphere, on this I can say it a manifold then. Yeah, it's on this manifold.
Tomorrow we're going to talk about this.
I steal your lectures somehow. Okay. So in this way, but the whole idea of this lecture, let me summarize my whole lecture in 1 minute, and then you can ask questions if you have. The idea was, in the first half of the lecture, I introduced you to the complex variables that you already know, just writing them in terms of the ordered pair, linking it with the Euclidean R2 space, and then by doing the multiplication, I told you that there is a difference between complex plane and the ordinary R2. R2 means Euclidean 2 by 2, two-dimensional plane. And then we have studied certain properties, associative, distributive, associative, and commutative of these complex numbers. Complex numbers are complex variables. I use these words, somehow back and forth. So, and then we have represented them in terms of the polar coordinates and calculated the geometrical formulas that of the sine and cosines that you have studied in your high school. And then we have calculated the nth root of a polynomial, and we found that these roots you can draw on a circle. And then, after that, what we have studied, we know that the complex plane is, if z goes to the infinity, it's very difficult to understand that. But there is a way of the compactifying it. After the compactification, what we have done is, we made a north pole, and we said that if you move your projection point closer to north pole, you will hit the point on this knife plane, which you call it as a z plane, to the infinity. And after that, on this longitude and latitude, you have calculated the distance, caudal distance, from one point to the other point in the hollow sphere. Suppose you have taken one point z1 on the longitude, the other point at the same phi, and then you have calculated the angular distance, which is 2 sine theta by 2. It was exactly s is equal to r theta for small theta. Right? If you have theta and you can just have 2 over here, so 2 over 2 is your r is 1, and because r should be equal to 1, because that's a unit sphere then. So what I told you, that any point that is on this circle of the equator, they will map, every point inside that will be mapped to northern hemisphere or southern hemisphere or from the south pole, whatever you say. So, and this way of projecting the planes from a complex plane to the Riemann surface is known as a stereographic projection. So thank you. If you have any questions, please.
What does the Riemann surface allow us to do later on? Like, what's the motivation behind defining it?
Motivation behind, Professor will talk a lot about it, whole manifolds, but this helps you to put infinity on a surface, honestly. Yeah, and that's a great advantage,
Yes.
On the North Pole, you have somehow the infinite.
Working with infinities on the complex plane, because we don't have to do that with extra.
Because there is no preferred infinity. In which direction you are working on a complex plane? You have a whole bunch of infinities. That is very uncomfortable.
So
You gathered everything and put that on a north pole.
from all the directions are mapped onto the north.
Exactly. That's the concept of
What
compactification.
happens at the south?
Because south pole is beneath you. You took two surfaces on the plane, right? So, by the way, you can.
Infinities mapped onto the
No. If you choose infinities on the north pole, then your south pole cannot map to infinity. That will map inside that surface. Because only one side that you can bring from infinity to that point, not all the sides, South is below, You choose a center and then you can map for all the sides. You can just fold all sides from the other and then you can make a sphere.
Is the Riemann sphere filled or is it
Hollow.
So
पैनकेक है सोचिए जाके पैनकेक है खड़े होके फोल्ड करना शुरू कर दे
See, there are only 2 degrees of freedom.
Exactly.
Here there are only 2 degrees of freedom here, x and y, and there only 2 degrees of freedom also, theta and phi. So
Okay.
Exactly.
Theta
Thank you.
and phi.
Yeah, because the constraint equation also says that
I
rho
was
1 rho 2.
simply thinking in terms of the plane and supposing that you could map the point. So what I was thinking was that there is the plane that you used to cut the sphere in the center, and
That was my Z plane.
is what we were trying to do was to map the entire complex plane onto the sphere that is hollow from the inside.
Imagine it's like this one.
it's a surface.
Surface,
You can
exactly.
say
That's
it's
why
a
Riemann
surface.
Yeah, that is why I said
Okay.
it's a Riemann surface.
So I cannot visualize like the points on the complex plane that lie in on the inside the sphere. It's like how where are they being mapped to?
By the way, what is a plane? Plane has only 2 independent axes, x and y, right? In a complex plane, I have kind of this spread. Every ray in any direction goes to infinity. I mapped it like this one. What happens if I insert a plane in it that has 2 dimensions only? So it means all the points, as Parvez said, there are 2 degrees of freedom over here. There are 2 degrees of freedom on the plane that I have inserted at the equator. So how these two degrees these two coordinates are mapped to the point on the plane which I have inserted that has only x and y axes. That is the whole idea. That is why I said that this is a Riemann surface. That nothing is in between. It's not. It's a plane. Plane has a 2 degrees of freedom. You can move x and y. But this is not x and y. This is x plus iota y. So
Where is the origin of the plane mapped to?
at the south
the equator?
pole, at the south pole. Which plane you are saying?
Yeah, I think there's a confusion here.
Visually confused.
So this confusion might be arising because you focused on the northern hemisphere and did not draw the line
On the
that
southern
maps for the yeah. So it's the same line. So it starts from the north pole. Yeah. So it's the same line. For mapping within the unit circle, the line is the same. So it starts from the northern hemisphere. It doesn't start from the southern hemisphere. Otherwise, it would be mapping again the points outside the circle. Yeah. So it's one line.
So you can approach north pole from 2 sides, this and that.
Yeah.
You said.
Thank you, Hassan. Thank you.
So the way I understood what you're saying is the reason why we make the Riemann surface is so that we can map all the points on the Z plane, containing all the infinities. But when we took the argument with the capital A, wasn't that the whole point, that we're confining our answers of the plane within, the reason why we take the argument is so that we don't have to go from 0 all the way from x pi. So we're not going to infinity over there. Isn't that the whole point of taking the argument?
That is theta, That is a theta. This theta has an argument business. This radius has no argument business. Radius is just 1. So this theta has an argument business in it. But I haven't specified any theta over here, you know. I have just written it in cosine and sine form, cotangent theta by 2. And I have just expressed it. There is no problem. Even on this surface, on this polar plane, for every single value of r, you have many possible values of theta. Do you agree to this point? Do you agree to this point? Because that is why you can make a circle. You have this point. All are at the same distance from the center, but they have different angles. So angle business is there. There's no problem in that. Absolutely no problem.
Again, if I may comment. So I think there needs to be another picture maybe, so to clarify the mapping. So it's from a plane, so that plane could be this blackboard, for example. So this is infinite plane, and then there is a sphere. I think we should put it somewhere else, and every point on that plane can be mapped onto this sphere. Okay, so these are two different surfaces. So it's a mapping from one surface, from the complex plane, to another surface that's a sphere. So yeah, we usually draw it that way. So
So the whole plane, you're saying it has infinite many values, and so we're mapping it to the Riemann surface. Doesn't the Riemann surface also have an infinite number of points?
It has infinite number of points.
So aren't we mapping like infinity to infinity?
No, but there is one thing that is very important. You know, every point of this plane has a projection on this surface, and the radius of the surface is 1. You know, that's the problem. You know the surface of this thing. I'm not talking about the angle. I'm not worried about it. I'm saying that every plane, including quote unquote infinity, has a projection over here, but point at the infinity in xy plane has this projection at the north pole. Okay. Yeah, that's why this is a continuous surface. Otherwise, we cannot draw the continuous surface otherwise.
Achha, so the point of the whole Riemann surface was to take infinity to one point, na? So there's only one way to approach infinity, right? But I don't see how we've changed it to only one way to approach infinity. You could approach infinity from here, from there.
You can approach from this side, anywhere you can.
So
all these
what's
points
the
on
point?
this plane from minus infinity to infinity, they are mapped to north pole.
Yes. So what's the point of doing the Riemann surface if there's still many ways to approach infinity?
You can calculate the distance, between the 2 points. That's a huge benefit, Otherwise, how you can calculate the difference between 2 infinitely for points?
Couldn't you do that like before on the 2D surface, xy plane?
How we can do it?
वही distance formula.
Distance formula?
Yes.
अच्छा.
Infinity minus infinity कैसे करोगे?
अच्छा.
Infinity इसको unit में measure कर रहे हो ना?
Okay.
You confused me so confidently, I thought I was wrong. Okay, so
you have to move on the surface. You can't cut this.
Okay.
You have to.
Geodesic.
Exactly. That's why I said geodesic distance. Thank you.
I think the point is that there's only one point on the Riemann surface that corresponds.
Exactly. There is only one point on this side. If I take the origin over here, and there is only one point on this side. So I can approach to North Pole from either side of origin. From the left side, on the Riemann sphere. That is only one point, which is a North Pole. Exactly.
So we're basically parameterizing infinity.
Exactly. By the way, this is a very powerful technique. When you do this conformal field theories and other stuff, then you can calculate this distance, and that comes 1 over z1 minus z2 to the power delta, something like that one, when you calculate the correlation functions. But that is a business for the particle physicist. For you guys, the only good thing to understand this mapping is the Bloch sphere and the spin system. It is given in every book. I guess in Zetley's book also it is given. I'm not sure about Lipov, but in Zetley's book it is given. So tomorrow I'm going to talk about, because now I have a concept of Z. We can make f of Z. And what are the conditions? We know that from the, I can give you the spoiler alert for tomorrow's lecture in 1 minute, You know that for ordinary function, if it is a function of x and y, then you can approach to 0. From delta x goes to 0, from left side and right side. And they should give you the same result, either you approach from the positive side or the negative side or the positive side. But on the complex plane, you have infinitely many directions to approach to that point. How you can calculate these derivatives then? By the way, the other important point in the complex variables that we have is, if we have first order derivative, then we can calculate the nth order derivatives also. That is without any problem. That might not be the case for the ordinary functions, because if function is x mod, then you can calculate the first x into x mod. You can calculate the first derivative but cannot calculate the second derivative, because on one side it is positive, on the other side it is negative. So I'll talk about these points in detail, and then the Cauchy-Riemann conditions. So tomorrow's lecture will be quite detailed and more mathematical. So thank you very much. Thank you for the patience.